right, let's get started. Hello, everyone. Welcome to the Consensus and Blockchain 1 session. We have two talks in this session. So the first talk is on Foundations of Platform-Assisted Auctions. The authors are Hao Chong, Ke Wu, and Elaine Shi. And Elaine will be giving the talk.
Okay, thank you for the introduction. I will be talking about auctions. Okay, so I was playing Wordle, and then I saw this ad at the top of the web page. It's apparently it's something called IQ Air. You can see like the air is angelic. It must be able to increase your IQ. Okay, so it turns out this ad is sold in a real-time auction hosted by Google. So in this auction, we have sellers and the buyers, but the sellers don't directly interact with the buyers. The auction is mediated by a middleman platform. In this case, it's Google, and we call this platform-assisted auction. Another example of platform-assisted auction is eBay auction. So what is the platform's role? The platform will get rewarded for providing various value-added services, like it provides rendezvous between the sellers and buyers. It provides functionality like product search, recommender system, and payment processing. Okay. So traditionally, when we design auction, we are used to thinking that the platform or the auctioneer is fully trusted. However, this is what happens in the real world. Like this is a famous lawsuit, Department of Justice against Google, and essentially Department of Justice is suing Google for manipulating their auctions. And if you look at this document online, you can see like Google is accused of various misbehavior, including withholding seller revenue, also injecting fake bids to raise the price floor, and many other more sophisticated strategies. So what this tells us is that we need to rethink mechanism design, where we don't just automatically assume that the platform or the auctioneer is fully trusted. So in particular, there is actually a gap between auctions on paper and auctions in the real world. So in the auction literature, we are very used to assuming, as I mentioned, that the auctioneer is fully trusted. We typically assume there is no collusion, and we assume it's a permission setting. In other words, we know a priori who are the setup participants. Whereas in reality, as we have observed with like these Google auctions, the auctioneer is not necessarily honest. So it's actually a trustless environment. And in particular, the auctioneer is in an advantageous position. It can also collude with, like, let's say, some of the buyers or collude with the seller to its advantage. And the auction actually is not permissioned. It's actually a permissionless auction in the sense that it's open. Anyone can join, and you don't know a priori how many people will join or who will join. And this permissionless nature also allows the platform to, or some bidders to post fake bids. Okay, so the question we want to ask is, what is a dream platform-assisted auction? What are the properties that we would like to have? So I will introduce a set of incentive compatibility properties, or IC for short. So at a high level, IC means that we want that the honest behavior be the best response or be the equilibrium of the protocol. Like it should be that in the equilibrium state, everyone wants to behave honestly. In particular, we want IC to hold for an individual buyer, and this is a classical property, and this is also what we ask for even in classical auctions. But here, because the platform is not trusted, we ask for more. Like for instance, we also ask IC for the platform. In other words, we want to make sure that the platform's best strategy is to honestly implement the auction's rules. Moreover, we want IC for platform buyer coalition. In other words, if the platform colludes with the buyer, the coalition's best strategy is to faithfully report the buyer's value and then for the platform to faithfully implement the honest auction. And in particular, in this talk, I will focus on coalition between platform and one buyer. And in the paper, we have some discussion about the case for multiple buyers. We want incentive compatibility for the seller. We also want incentive compatibility for platform and seller coalition. In other words, if the platform colludes with the seller, the coalition's best strategy is to behave honestly. Okay. So notice that the correlation resilient properties are also centered around the platform because we want to focus on these notions that capture the idea of antitrust. We don't want the platform to become a monopoly. Among all of these properties, except for the first property, all the other properties are new and they arise because the platform is not fully trusted. So I also need to mention the strategy space when I define the incentive compatibility. So we are going to assume you can misreport our input, you can overbid or underbid, you can inject fake bids, and this is a property of permissionless because you don't know the identities ahead of time. And if you are running, let's say, a cryptographic protocol, you can also just deviate arbitrarily from the protocol. So all these strategies are possible. I am going to put in an assumption. This detail is mostly not important for the rest of the talk, but it actually may arise in just one place. So we are going to assume the platform cares about its reputation and it's not going to deviate in ways that leads to detection. Like for instance, if I'm going to claim the auction's outcome is not even in the output range of the auction, that can easily be detected. So we don't consider such strategies as valid strategies. And in fact, if you consider this as a valid strategy, our prior paper in Soda shows there's a very strong impossibility result. Okay, so the first question I need to answer to a crypto audience, and I think we are all trained to first think about throwing some powerful cryptographic tool at this problem, right? So why not just use MPC and maybe MPC will just magically solve the problem? Is this the case? And we can actually look at a strawman example to answer this question. We are going to think of MPC not using the real world perspective, but using the ideal world perspective. And we can do this because of this very nice simulation paradigm. So we can think about implementing an auction, essentially the second price auction using MPC. And the second price auction works as follows. In this case, let's imagine the simplest example. There's only one item, and you sell it to the top bidder, and it pays the second price. Sorry, there's only one person here, so really just the winner pays the second price. And the platform's going to get, let's say, for the sake of argument, I'm just going to put in an arbitrary number. Say the platform gets 10% of the revenue, and the rest of the revenue goes to the seller. So if we use MPC to emulate this ideal auction, it's actually not a good auction because, let's say, if the platform colludes with some buyer, let's say Shafi, then the coalition can benefit by overbidding. And the idea is, so here's a simple example. Suppose there are two buyers. Shafi's true value is 5 and Dan's true value is 8. So Dan is the honest user. Normally, Dan should get the item and he should pay the second price, which is 5. But notice that the platform is getting 10% of the revenue. So if Dan pays more, then the coalition can gain more. And as a result, it is in Shafi's best strategy to bid not her true value 5, but something higher. So let's say if Shafi bids just like slightly smaller than 8, then Dan will pay essentially almost 8, and then the coalition's revenue will be higher. Okay, so this is an example where overbidding can help. I mean, of course, because we are running the auction using MPC, it's not necessarily the case that Shafi will know what Dan's true value is, because it's not like Dan is submitting his bid in the clear text, right? He's going to, in MPC protocol, you submit your bid in secret share format, and Shafi may not know your true value. So imagine a case where Shafi doesn't know Dan's true value, but she knows Dan's value is distributed uniformly between 0 and 10. And actually, you can still perform the same overbidding attack. You can actually calculate in expectation what is the optimal price you should bid to, in expectation, optimize your gain. And it turns, I'm not going to show the calculation, but the conclusion is that Shafi should still bid slightly higher than her true value to optimize the coalition's gain. Okay. So what we learn from this example is that just throwing MPC at the problem doesn't solve the problem. In particular, MPC does a good job at defending against arbitrary protocol deviations, but it doesn't protect against misreporting input. I mean, because misreporting input is a strategy even in the ideal world. In this case, there are, to misreport input, you can overbid, underbid, you can also inject fake bids. Okay, so in order to be able to answer this question, we then need to take a code design perspective. It's crypto meets mechanism design. This is also a special case of a line of work called decentralized mechanism design. It's called decentralized because we no longer have a trusted auctioneer or trusted platform. So let me talk about our results. I will first show an inefficient MPC-based solution. I will then talk about some fundamental limitations. And finally, I will tell you how to make the protocol more efficient using a new simulation notion called utility-dominated emulation. Okay, so how can we design a dream auction? I will start from the strawman I've just mentioned, and let's fix it together. So how can we fix this strawman? I'm going to suggest 3 modifications to the protocol. First, we are going to introduce a reserve price called R, and you have to bid at least R to be eligible. If you bid less than R, you are not considered eligible. And the sales price is just K plus first. Oh, so here I'm generalizing the auction to K identical items. It's not just a single item. And so basically you sell to the top K bidder and they pay the K plus first price or R, whichever is higher, because R is like a price floor called the reserve. And previously we had this overbidding attack, and it was because platform was getting 10% of the revenue. So let's now say the platform will get nothing. So actually, when I say nothing, it doesn't actually have to be absolutely 0. It can be any constant, as long as the constant is fixed and independent of the outcome of the auction. Okay. And the third modification is I will require that you broadcast the result, the final price to everyone. So everyone should have the same view of the final price. And I will explain why each modification is important. And the way I explain it is like we can just walk through all the properties and try to prove them together. And in the process, we'll understand why each modification is important. So first, it is trivial to show the auction is buyer incentive compatible. And because this we know from classical mechanism design literature, that the second price auction with reserve is incentive compatible for the buyer. So there's nothing new here. It is trivial to show its platform incentive compatible, because the platform just always gets nothing no matter what it does. So of course, its honest behavior maximizes the platform's profit. So I want to show that it's incentive compatible for the platform buyer coalition. And this is more interesting. So first, if the platform forms a coalition with the buyer, because the platform gets nothing, the coalition's best strategy is to help the buyer, right? In order to maximize the coalition's gain, they should help the buyer. And earlier, we have established that the buyer alone cannot do anything interesting to help itself. So really, whether the platform can help the buyer boils down to this question: what can the platform do for the buyer that the buyer cannot do on its own? And once we understand the question, we just have to show that our auction defends against this kind of strategy. So what can the platform do for the buyer? Indeed, there is something that the platform can do, and this is why we need to introduce this broadcast to prevent it. And I call this the partition world attack. And this partition world attack, actually in consensus law bound proofs, you also see this kind of attack a lot. So imagine platform is colluding with Shafi. Shafi has a true value of 8. Dan is the honest user with a true value of 10. There's a single item, the reserve is 0. Normally, Dan should get the item and pay a price of 8. But in this attack, the platform will pretend there are 2 worlds. So somehow it will like spawn 2 instances of MPC, and Dan thinks it lives in a world with a high bidder, but that's a fake bid. So Dan thinks he has lost the auction, and he didn't get the item. And this allows the platform to give the item to Shafi. And because Shafi is in her own world with no other competing bid, so she will get the item and pay a price of 0. But this attack can be prevented by broadcast. Like if you are required to broadcast the final price to everyone, and if the platform still launches this attack, it cannot provide a consistent explanation to both the seller and Dan. Like to the seller, it has to broadcast the price of 0, right? Because it's selling to Shafi at the price of 0. But then if it also tells Dan the price is 0, then Dan will notice there's something wrong because he should have got it if the final price is 0. So this is where I mentioned like we only consider safe strategy. So this strategy is not safe. And that's why broadcast can help prevent the partition world attack. Okay, so it turns out that we can formally prove that in some sense, this is the only interesting thing the platform can do. And if you introduce this broadcast, then indeed the protocol is incentive compatible for buyer platform coalition. So now let's look at incentive compatibility for the seller and platform seller coalition. And here the main concern is that the seller can inject a fake bid to raise the price floor because the seller is getting the revenue, so it's interested to get more revenue. And the fix is to introduce the reserve, and you can think about it in this way. The reserve is like, I'm going to calculate for you what is the optimal price floor, and I'm just going to bake that into the mechanism. And because it's already baked into the mechanism, then it's not helpful for the seller or the coalition to inject fake bid anymore. Okay. And as a byproduct, actually, this auction is also revenue optimal because of the use of the optimal reserve. And here I want to quickly mention that the privacy of the MPC is important for these properties to hold, because if people just submitted their bid in the clear, then you can inject a fake bid a posterior. Like you can look at what other people are bidding and then inject a fake bid that's optimized for the setup bid. But whereas with MPC, you cannot see what other people are bidding. All you know is a priori distribution on other people's bids. And that's why you can calculate what is an optimal price floor in expectation and bake it into the mechanism as a reserve. So actually in our paper, we also proved that in some sense, this privacy is necessary. If like everyone just reveal their bid upfront, then it's not possible. I will not even formalize the impossibility here. Okay, so this is the summary. Like we have a very nice auction with all these dream properties, but this auction is not without limitation. Like we have several questions. Like one is that the fee structure is very restrictive. The platform has to basically get constant revenue. Can we have a different fee structure? Also, can we avoid this broadcast? Because in practice, if you want to have broadcast in a permissionless world, like one way is to use a blockchain, but posting messages to the blockchain is quite expensive. You have to pay gas. So can we avoid this? And finally, we are using generic MPC. So can we make the protocol more efficient? It turns out we proved that the first two goals are impossible. I'm not going to elaborate on the proof in the interest of time. And then for improving efficiency, we show that, yes, it is indeed possible. And we introduced a new simulation notion called utility-dominated emulation to improve the efficiency. So let me just quickly mention how to improve the efficiency. If you use any generic MPC using best known technique, the overhead will be quadratic in n, which is the number of buyers. And this is because in this auction, everyone has a different output. So even if you use something like FHE, you still have to help everyone threshold decrypt their output, which results in the quadratic overhead. If you use powerful tools like indistinguishability obfuscation, there's some hope of reducing the communication to quasi-linear, but it's not known how to reduce the computation. Computation is still quadratic. So it seems like we may want to get rid of the MPC, but MPC does provide a very nice design paradigm, the real world, ideal world design paradigm, because anytime I talk to mechanism designers, like they're very excited about the use of cryptography in mechanism design, but they don't know how to think about crypto. So the most common question I get is, how do I abstractly think of cryptos as an ideal box so I don't actually have to work with the cryptographic details? And the MPC paradigm lets the mechanism designer just work in the ideal world, and the cryptographer can worry about how to generate the real world protocol. So we want to preserve this paradigm, but we want to improve the efficiency. And then how can we solve this dilemma? We will introduce a new simulation paradigm called utility-dominated emulation. At a high level, this notion says that any real world strategy is utility-dominated by some ideal world strategy. And we show that if the real world protocol is a utility dominated emulation of the ideal world protocol, then any incentive compatibility property you have in the ideal world will translate into the real world. So preserving this very nice design paradigm. And under this relaxed notion, we can design an efficient protocol that is quasi-linear overhead. And it's also constant number of rounds and only relies on constant number of broadcasts. And as I mentioned, the broadcast is unavoidable. There's an impossibility result without broadcasts. Our paper has more details. It actually even has more results. I didn't have time to even cover all of our results. And this is obviously just tip of the iceberg. Since this is the blockchain session, my talk has to mention blockchain. So here it is. Like decentralized mechanism design is also the biggest, most exciting problem in the blockchain world today. Because of this, you may have heard of this phenomenon called MEV. And then the blockchain community is like very insistent on mitigating MEV. And for these blockchain questions, like oftentimes even it's not even clear what is the right notion, right? So this is kind of like a new field, and it requires the intersection of crypto and mechanism design, and that's why I find it exciting. Thank you.
Thank you, Elaine, for the wonderful talk. We have time for one quick question, perhaps.
Yeah, thanks. Very nice. You said that sort of the seller has to set the reserve price in a Bayesian way. Is the sort of lack of fairness of MPC an issue? Like, could a seller auctioneer coalition make the auction fail, and then the seller knows the bids because of the lack of fairness of MPC, maybe? And then it can later on adjust its reserve price.
So we are assuming if it fails, everyone gets zero. So it's not incentive compatible for the coalition to make it fail. We are. I guess you are saying, you know.
Again, then usually it would be repeated, right, in the real world.
This in our paper we are considered like single shot.
Okay.
And I think in general, it is an interesting question, like what if you have repeated auction?
Right.
So our paper doesn't answer that, and I think that is an important open question for future work.
Okay, thanks.
Okay, let's thank Elaine again. So our second talk of the session is Merkle mountain ranges are optimal on the witness update frequency of cryptographic accumulators. This is work by Joseph Bonneau, Jessica Chen, Miranda Christ, Joanna Curran-Tidal, and Miranda Christ will be giving the talk.
Okay. So thanks everyone for coming. I will be talking about cryptographic accumulators, specifically Merkle mountain ranges. And a problem that they're often used to solve is where you have some large and growing set S. You can think of this as storing maybe a large set of all registered users in your system, maybe internet certificates, or all transactions on the blockchain. So this set is very large and will continue to grow. And an accumulator lets us store this set in a very short commitment. So you can think of this as being polylogarithmic in the size of the set. And it also gives us some membership witnesses for everything in the set. And so typically this commitment will be publicly posted somewhere on some bulletin board, and the witnesses will be distributed to individual users who care about the elements in the set. So for example, if we're storing the set of all registered users, each user will be given a membership proof to prove that they are registered. And so accumulators let us verify membership very efficiently. Given just an element, xi, and its corresponding witness, anyone can take the commitment to the set and check that xi is indeed in the set. So this verification algorithm outputs true, xi is in the set, or false if it's not. Okay, and so just to reiterate the syntax of a cryptographic accumulator, we have some accumulate algorithm that takes as input a set, outputs the commitment and membership witnesses, and the verify algorithm that outputs true or false. And accumulators have two important properties. First is completeness, which says that proofs of things that were actually in the set should verify. And soundness says that it's infeasible to find a verifying proof for something that was not included. And a common solution for accumulators is what's called a Merkle tree, which you've probably seen. And here we just store the elements as the leaves of the tree. The root is the commitment, and the membership witnesses are the siblings along the path from the leaf to the root of the tree. Okay. And so in our setting, we care a lot about what happens when we add an element, because if somebody's membership proof changes, it means that someone has to go and redistribute these fresh proofs to everyone. So this is quite costly. And with Merkle trees, if we add an element, actually the membership proofs very often change. So before X1 had this membership proof shown, and we can see that when we added X4, it actually changed. And in fact, for Merkle trees, if you add an element, nearly all other elements' membership proofs will change. So while Merkle trees have a short commitment and fairly short membership proofs, they don't do so well in terms of the number of witness changes. Okay, and just to drive home what a witness change is, you can look at the witness of X1 as we accumulate a growing set. So here, say we accumulate just X1, we start with some witness and some commitment, and this witness verifies for this commitment. But if we add another element X2, we get a new commitment. We don't know for sure whether this old witness for X1 still verifies. But here we got lucky and it did. But you can imagine as we add X3, we get a new commitment, and now the old witness no longer verifies. And so as you repeat this process, sometimes it'll still verify, sometimes it won't. And the number of witness changes is just the number of times we had to change the witness for X1 throughout this whole process. So here we had 2 witness changes. And if you want to minimize the number of witness changes, but still have a small commitment, there are a few solutions that you could try at first. Maybe the most obvious solution is just a simple database where you store the entire set in full. So here the commitment has size O of n. And now there are no witness updates required because there are no witnesses at all. You just check if something is in the set. But okay, we want to do better than this. And sort of on the other side, we saw a Merkle tree, which has a very short commitment, a constant size in terms of the size of the set. But on the other hand, we need to update witnesses nearly every time we add something new to the set. And you could try to do something in the middle, where maybe you take k Merkle trees, so you partition the set into k sets of equal size. Now you have k commitments, and you only update witnesses n over k times whenever something in its own tree is added. But this isn't much better. So an obvious question is whether we can have something non-trivial in the middle here. Ideally, we want a polylogarithmic size commitment and substantially fewer than n over k updates for the witnesses. And as I mentioned, these witness changes are really costly in practice. And so in fact, this problem has come up in practice. And it's led to sort of the reinvention of the Merkle mountain range. Which I'll explain in a minute, but I just want to point out that this Merkle mountain range has occurred in several different applications. It was first invented by Todd in the context of blockchains. It's also come up in the context of distributed PKI and registration-based encryption. And so all of these different areas are converging on the same object to solve the same problem, and this is the Merkle mountain range. Okay, and to give a quick overview of what a Merkle mountain range is, you can think of it as a list of Merkle trees of doubling size. So you might have a tree of size 4, size 2, and size 1, and I'll show you how we update these trees as we add elements to the set. So here right now we're storing a set of size 4, but we want to add a 5th element. And so what we do is we add it to the lowest empty tree, which is this tree of size 1. Now, if we add another element, the tree of size 1 is now full, so we merge x5 and x6 into a tree of size 2. And if we add again, we add it in the tree of size 1, and so on. So if x8 came along, now we would merge that in x7 into a tree of size 2, and then continue merging and end up with a tree of size 8 that I didn't want to make on the slide. Okay, but What I want you to see here is that once an element ends up in the largest tree, its witness isn't updated very often, right? Like as we're adding new elements, they get added to the smaller trees. And so this results in fewer witness updates. An element's witness only changes when its tree is merged, which is much less often than we saw for regular Merkle trees. And it turns out that for binary Merkle trees, each witness changes log n times as we accumulate a set of n elements. And you can in fact do better than this by taking a log n array Merkle tree. So if you take the branching factor to be log n, you can now have witnesses change only log n over log n times. So this is a pretty nice witness update frequency, and this maybe explains why Merkle mountain ranges have arisen so much in practice. Okay, so we filled in our table a little bit. We have Merkle mountain ranges between the K Merkle trees in the simple database. But really, we might want to do even better, right? Like people have tried hard to come up with solutions for this problem. They all arrive at the Merkle mountain range. Is this the best that we can do? And so the question that we answer in this paper is exactly that, and we prove that in fact you cannot do any better than the Merkle mountain range. If you want a succinct commitment, most membership witnesses need to change a super constant number of times. Okay. And as stated, this isn't yet tight with Merkle mountain ranges, which achieve log n over log n. But we strengthen this result to show that for accumulators that satisfy a natural notion of sub-exponential security, which Merkle mountain ranges do, then most membership witnesses must change log n over log n times. And so this shows that log n array Merkle mountain ranges are essentially optimal. Okay, and so for the rest of this talk, I will try to give you just a taste of our proof techniques by giving a proof sketch of a much weaker result than what we show in the paper. So in particular, I will show you that if the commitment is succinct, then at least n over log n witnesses must change at least once. So this is very weak because it doesn't show that any witness must change multiple times. And in the end, we want to show that most witnesses change even log n over log n times. But I just want to show you the kinds of techniques that we use. Okay, and I'll show this by a compression argument. So the framework for this argument is we'll consider Alice, who wants to send some information to Bob, and she's going to use an accumulator to encode this information. And the idea is going to be that if this accumulator has too few witness updates, then Alice will be able to communicate this information more efficiently than should be possible, and will arrive at a contradiction. Okay, and so what Alice is going to try to communicate is a random subset S of x1 through xn. So Alice and Bob both know x1 through xn, and Bob wants to know what subset of these Alice chose. So his goal is to recover S. What Alice is going to do is she'll use her accumulator to get a succinct commitment to S. And as she's doing this accumulation, she'll also remember which elements witnesses change at least once. And she'll write all of these elements in a list L. Now she'll send both the commitment and the list to Bob, and Bob is going to try to recover S using only this information. So what Bob is going to do is he's going to keep in his head a set S prime of elements that Alice has added to her set. So he's going to go from x1 through xn, maintaining the set of what he thinks Alice has added so far. And for each next element xi, he's going to test whether Alice added that. And the way that he'll do this is he'll accumulate everything he thinks was added so far, along with xi, to get a commitment, which he won't look at. What he really cares about is the proof pi I for xi. And what he'll do now is he'll check whether this proof still verifies against the end commitment that Alice sent. And if this proof doesn't change, then that exactly means that it still verifies against the end commitment. And in this case, Bob can go ahead and add xi to his set. On the other hand, if this witness did change, then it means that Alice wrote it down in her list L. And so Bob just looks at the list, and if it was included in the list, he also knows that Alice must have added it to the set. And so we can formalize this argument and show that soundness implies that Bob will never add something to S prime that Alice didn't actually add to S. And completeness plus this helper list that Alice sent ensures that Bob actually does add everything that Alice added. Okay, so we've shown that Alice is able to successfully send this information to Bob, but what we need to show next is that if the accumulator is too efficient, then it breaks information theoretic bounds. And so what we need to do is count the number of bits that Alice sent versus the amount of information she's able to encode. So in total, she sent the size of the commitment plus the size of the list number of bits. This is dominated by the size of the list, which is like log n times the number of witness changes bits. On the other hand, Alice communicated a random subset of a set of size n, and so she sent linear and n bits of information. And doing out the algebra, this means that the number of witness changes must be at least n over log n. Okay. So what I've just shown you is that some witnesses have to change at least once over the course of this accumulation. But as I mentioned in the paper, we want something much stronger. And the key technical challenge here is to boost this argument to say that most witnesses change many times, not just once. And I'll give just a hint of what we do here. The key idea is to iterate this compression argument that I just saw you, applying it to, instead of accumulating elements, accumulating accumulators. And so this kind of lets us apply this argument to the same element multiple times as it is accumulated within different accumulators. And in the end, we'll have each element participate in a super constant number of applications of the argument. And so this is how we show that it must have a super constant number of witness changes. Okay. But in applying this argument, there is kind of a blow up in the complexity, and we start to come up against the soundness bounds. And so the reason why we get a stronger bound when we have sub-exponential security is it lets us do more applications of this argument before we run up against the soundness bound. So that's very high level, but that's kind of the idea of how we can boost the argument. And for the full details, I encourage you to see the paper. Okay, so what I've shown you today is that for the problem of witness update frequency, Merkle mountain ranges are essentially optimal. Any accumulator with a succinct commitment has to have a super constant number of updates per witness. Thank you.
Elaine, you have a question?
I just have a comment. I guess like maybe the Bentley Sachs first came up with it in 1970s. They described it as a generic approach that can be applied to any data structure. So like maybe Todd is not even the first who came up with it.
Oh, wow, okay, thanks.
Great research and proof. Did your team consider what proofs could be made about exclusion proofs, given that like Merkle mountain ranges deal with like inclusion proofs?
Yeah, that's a good point. So I will say our bound applies immediately to data structures that provide both inclusion and exclusion proofs, because it applies to anything that provides inclusion proofs. So if you have exclusion proofs as well, then it still applies. I haven't gone through the details, but I would expect that it also applies to things that have only exclusion proofs. But yeah, we didn't think about it too hard.
Thank you for your talk. And then, so last slide you mentioned about like accumulating the accumulator means like accumulating the multiple MMRs, right? Or is it like the different data structure like from the MMR?
We consider any accumulator. I guess Yeah, we consider any accumulator. It's not specific to MMRs. And within the argument, we use that accumulator to accumulate commitments generated by itself earlier.
Oh, I see, I see. So what I experimented before was like having multiple MMRs and stacked together so that like reduce the duplicated like paths. And that is kind of optimal in the case of like having a multiple MMRs to like accumulate. So I'm just wondering if you checked this case.
We didn't think about that specifically, but like anything that fits this functionality of an accumulator, our lower bound does apply to.
I see, I see. Yeah, okay.
We have time for one last question.
Hey, cool work. I was wondering if the bound is sensitive to the notion of membership security. So there's weak membership and strong membership security. One says the digest is produced honestly, the other says it's produced adversarially. I wonder if that affects the bound in any way.
I would need to check the details, but I think it does not affect the bound because in our like communication game, Alice is not adversarial. Like as long as she can communicate the information to Bob, then the argument goes through. And so she just needs to form the accumulator honestly and Bob will be able to recover the set. So as long as Bob, when trying to test these proofs, doesn't accidentally stumble upon a proof for something that wasn't included, then it goes through. And so since Alice forms the commitment honestly, we're in the setting of security, I think.
Cool. Thanks.
Okay, let's thank Miranda and Elaine for the great talks.